Okay, moving on to question 3 now. All right, it's given us the mass of the ball, so let's write that down straight away. So m equals 0.60 kilograms. Okay, and it's asking us to calculate the weight of the ball. Okay, and hopefully you know an equation that links mass and weight together. It's that W equals mg. So we know the mass from the question. That's 0.60. Okay, and then G, if you go back to the beginning of the paper, look, it says, where necessary, assume that the acceleration of free fall G is 10 meters per second squared. Okay, or 10 newtons per kilogram. Okay, so back to this question, wherever it's gone, here we go. G is just 10. Okay, and that makes 6 newtons. Again, we need to make sure that we've put the units. Double check. Okay, formula, substitution, answering units on the same. So yeah, I'm going to score 4 marks for that question. It makes a normal contact force with the ground, and this force is equal to the weight of the ball. All right. So what is the size of the force that the ground exerts on the ball? Okay, well, it tells you the force is equal to the weight of the ball. Okay, so it's going to be the same as the weight of the ball. Right? That's it. Okay, and if we think about it, it's because, you know, the weight of the ball downwards, 6 newtons, okay, is going to be the same as that contact force upwards, 6 newtons, because the ball is currently stationary, right? Okay, during practice, the student practices shooting vertically, and then we've got to calculate the initial velocity of the ball. All right. So let's think about what we know from the question. We know the height, so that's the displacement, so that's going to be 3 meters, right? Okay. We know the acceleration. Okay, that's g. Okay, is the acceleration. And we looked that up just a moment ago. That was 10 meters per second squared, right? Okay. Now at the top of its flight, okay, we know that the final velocity, once it gets to the apex of its flight here, then the final velocity is going to be 0 meters per second, right? And the question's asking us to calculate u, which is the initial velocity, right? So the formula that we're looking for here, and hopefully you worked it out already, is v squared equals u squared plus 2as. That's the only formula that connects those four things together. Okay, so v is 0, so 0 squared is 0. The u is the thing that we're trying to find. Okay, and then we've got to do plus 2 times by the acceleration. Now, the acceleration is if the displacement is upwards, then the acceleration is downwards. So right, so we need a minus sign in there to make this all work, right? So in brackets, I'm going to put that as minus 10. Okay, and then that's times by the displacement, which is just 3. So if we look at the right hand side of the equation, okay, then I've got 0 equals u squared minus 60. So that means that u squared, add 60 to both sides, u squared is 60. Okay, and then I've got to take the square root of that. So u is the square root of 60. And if you do that on a calculator, you'll get 7.7 meters per second. And they've already given you the units there, so no need to write the units in as well. Let's check. I've got a formula, I've got a substitution, okay, and I've got my answer, and they've given me the units, so I should be scoring 4 marks for that question. So now the ball's moving downwards. What is the effect of increasing the downwards resultant force on the ball? Okay, well, if we've got a ball and it's got a resultant force, then sigma F equals ma. If we increase this side, right, and the mass stays the same, so that's constant, then that means that the acceleration is also going to increase. Okay, so if you've increased the acceleration, then that means that it's going to decrease the amount of time it takes for the ball to bounce back to the student's hand. Why? Because now it's going to be covering, the rate of change of speed is increased, so that means that it will reach a higher speed, so that means it will take less time. State the law of conservation of energy. Okay. There's several ways that you can do this. I think the most elegant way of doing it is saying that sigma EI, which is the total initial energy, is equal to sigma EF, which is the total final energy. The other way that you can do this is, of course, to say that energy cannot be created or destroyed, but it can only transfer from one energy store to another. Two energy changes that occur when the ball hits the ground. Now, look, they've put this in bold, so this is important, right? So we're not talking about as the ball is falling. As the ball is falling, then its GPE store, when it's at the top, is changing into a kinetic energy score as it falls, all right? But this is the point where it hits the ground, okay? So what's going to happen when it hits the ground? Well, the first thing that's going to happen is that the kinetic energy store, okay, because it was moving fast, is the kinetic energy store is going to decrease, okay, because it decelerates rapidly as it hits the ground. Another thing that could happen is that the ball will deform. So instead of being a nice round ball like this, okay, when it hits the floor, it's going to kind of squash down like that. So that means that the elastic potential energy store, okay, is going to increase, okay. Another thing that happens when the ball hits the floor is you're going to get some sound radiated away, okay, so you're going to get some sound radiated away from the ball, and some of the energy will be taken away in the form of sound. And then the other thing is, you might have experienced this with like a squash ball or something. At the end of a game of squash, the ball is very warm. Okay, why? Because it's constantly being squashed and stretching back to its original shape. So that means that the thermal store of the ball will also increase. And that's the end of question 3.